All right. So today's lecture, we've discussed quite a bit on amplifiers, and we know that amplifiers require biasing. This is our prototype amplifier, and they require biasing. The transistor requires biasing in the active mode, and we define our bias point in terms of the collector current and the collector emitter voltage. And we have seen that the bias point is very important. For example, we have seen this expression for voltage gain. We have seen that voltage gain can be written. One of the expressions for voltage gain is VCC minus VCEQ by VT, where we directly see that depending on how I choose my bias point, VCEQ, my open circuit voltage gain depends directly on it. So one can see the importance of VCEQ. Input resistance we know is important. You can see input resistance is inversely proportional to ICQ. So a value of ICQ directly determines how much input resistance you can get. Both of them, ICQ and VCQ, determine, in the last couple of lectures we were seeing, they determine the output swing. So in a way, all that is illustrating is that the amplifier's performance, whether you take gain, input resistance, maximum voltage swing, we look at frequency response, you look at noise, all the amplifier's properties, they depend on where you bias it, ICQ and VCEQ. Now, obviously, if ICQ and VCQ then change, then everything in terms of amplifier's performance changes. So naturally then, we are interested in the stability of the bias point. If the bias point is not stable, I make 100 amplifiers or 1,000 amplifiers, and each one's bias point is different, then each amplifier's performance will be different. Okay, and therefore that creates a problem here. So what are the things that cause bias point to deviate from what your intention is? Well, I've listed a few of them. Supply voltage. We are talking about ICQ and VCEQ. The currents that you see here, the voltages that you see here are derived from supply voltage. And we know that the supply voltages can vary. I mean, when I say 5 volt, it may not be exactly 5 volt. It may be plus minus 5% or 10%, a little bit higher or a little bit lower. And variations in supply voltage can cause ICQ and VCQ to vary. So that's one thing to watch out for. The other thing is, even if your power supply that you see here, VCC is ideal, is constant, what may happen is that when you have a complicated circuit, the power, as you know, is coming from one particular pin of an IC. The power is coming from one particular pin of an IC, and the power is routed and eventually comes to your, to this amplifier. And as the power is routed, that VCC point from your input is routed and brought to your amplifier, there's a bit of resistance involved. Any conductor or whatever that I use, there's a bit of resistance involved. And because of voltage drops in that particular resistor, then what may happen is that the power supply that you get here may be a little bit different. Not only that, there may be a little bit of noise in the power supply. To this power supply that you see here, some digital block or something else may be connected. And as the digital block switches, as your inverters and AND gates and all that, as they switch from on state to off state, they draw current. And the current has transients in it. And those transients may cause VCC to vary. There may be a slight ripple or slight noise into this particular supply voltage. Now, if that noise, whatever variation in VCC may cause variation in ICQ, VCQ may cause variation in gain and other things. Anyway, so supply voltage is one source of variation. Temperature is always there. We have seen that as you vary temperature, at least 3 things happen when you vary temperature. One of them is that the base emitter voltage that you see here, base emitter voltage, that changes. We saw that it decreases by 1.8 or 2 millivolts per degree Celsius. So base emitter voltage varies. The other one is as you vary temperature, the beta changes. Beta becomes higher as the temperature becomes higher. So that changes here. And then all the resistors that you see here, they're all temperature dependent as well. So as temperature changes, the values of the resistors, they all have a temperature coefficient. So that also changes. So all of that is a source of variation in bias point. The most dominant one, at least for BJT amplifiers, is that the current gain beta. The current gain beta, you see supply voltage may change by 4-5% or whatever. Temperature changes, but base emitter voltage only changes by 2 millivolt. But the current gain beta can change a lot. The nominal value of current gain beta may be 100, but you may end up getting 150, may get up 200, maybe 50. So that's something that varies quite a bit. And so if your bias current depends strongly on the beta, then you're in trouble. Your bias current and voltages then would vary a lot, and then amplifier performance would also vary. As an example, we can see here this very simple circuit that we have talked about. So ICQ is basically what you do is you calculate the base current. So VCC minus VB by RB is the base current, and base current you multiply by beta and you get ICQ. So when we talk about variations and we talk about stability, we calculate this quantity. Stability we define as a quantity called S, and X depends on stability with respect to what? What is it that is changing and causing changes in the current? So we define it as the percentage change in collector current divided by percentage change in the variable that is causing the variation here. For example, if I'm talking about supply voltage, so I would define stability with respect to supply voltage as change in current, percentage change in current divided by percentage change in the supply voltage. And it's easy to differentiate this and calculate and show that this is equal to VCC by VCC minus 0.7. So stability S then is if VCC is significantly larger than 0.7, then this is practically equal to 1 or 100%. Okay, a little larger than 100%. So 10% change in VCC will cause almost like 10% change in collector current here. So that's a fairly sensitive circuit. 100% sensitivity or sensitivity equal to 1 is a fairly very sensitive circuit. Okay, so that's not a good feature of this particular circuit here. Similarly, we can calculate stability with respect to VBE, the base emitter voltage here. Stability with respect to VBE, why? We know that temperature may cause changes in VBE. So stability with respect to VBE, simply you can define and calculate it to be VB by VCC minus 0.7. And you can see why we want supply voltages to be large. Because VBE, you know, is roughly 0.7. And if I make supply voltage 12 volt, then this quantity becomes small. And therefore, any change in VBE due to temperature and all that will not result in such a large change in the collector current. Okay, so for that reason, you would like to keep VCC large here. You also see that if I have VCC, if I'm running it on a 1.5 volt battery, if this is 1.5 volt, if this is 1.5 minus 0.7, that gives you 0.8, and this is also 0.7 by 0.8, roughly 1. So when you are running your amplifier on 1.5 volt, you see that stability with respect to VB is very small then. It's 100%. Okay, so that's a problem. If you want to run your amplifiers on very low voltages, you can see that their sensitivity to, for example, VBE, which means sensitivity to temperature, becomes large. But as I said, compared to all of these, the one that matters the most is the current gain beta. And in this case, we can define stability with respect to beta, same thing, percentage change in current divided by percentage change in beta, and you'll see it's 1. So stability with respect to beta, if you double, obviously, if you double beta, you double the ICQ. Or if you half beta, you half the ICQ. So that's a bad feature. So if we look at this particular circuit here, you can see stability with respect to VCC is poor, 100%. Stability with respect to beta is also 100%. If we look at this, only if we use large value of VCC is our stability better here. Now, I'm not going to spend time, this is an introductory course, I'm not going to spend time on how to design circuits which are independent of supply voltage or temperature. I'll focus more on beta because that's the one of the most important variables here. But before I do that, just as a brief example of how can you make something which is independent of supply voltage. Look at this particular circuit. Let's see whether this particular circuit, do you think, will the collector current of Q3 depend on supply voltage? collector current of Q3, first order. Collector current of Q3. So if you note, if we look at this particular circuit, I have R1 and some VCC, and so it biases these transistors here. So the voltage at this particular node will be 0.7, roughly 0.7 here, and another 0.7. So the voltage at this particular node is 1.4. So 1.4 comes here, and then another 0.7 drops here. So the voltage at this particular node is 0.7. And so the current flowing here in this particular transistor would be 0.7 by R2. Now, whether this is 5 volt or 3 volt or whatever, the voltage here would be pretty close to 0.7. And so the current that is flowing in this particular transistor would be 0.7 by R2. So I can change my supply voltage by a lot, from 5 to 6 to 7 or whatever. This voltage is not going to change much. Obviously, what will happen is as you change the supply, the current here changes. And these 0.7 and all that I'm talking about are not exactly 0.7. You know that the base emitter voltage depends logarithmically on the current. So as you change the supply voltage, these voltages will change, but logarithmically. Okay, so very weak dependence, and therefore this voltage has a very weak dependence on the supply voltage, and you get a supply independent current. So there are techniques whereby you can get supply independent current, where you can get temperature independent current, and then this particular current that you get here, as I said, I'll not go into the details, but one of the homework assignment was that from one current you can generate many other currents using a current mirror, and therefore for biasing you can use this supply independent current, and you can use it for biasing your circuits elsewhere in your system. Anyway, so as I said, there are techniques for making supply independent current, temperature independent current, but the focus of our work is on basically on the beta. So we want to, before we go into those features, we want to handle beta and make our circuit insensitive to beta here. So this is our default circuit, and we would like to improve our circuit. So this has 100% beta sensitivity, as you can see here, and we want to improve things. Now, if you recall, one of our homework assignment was also, if you note that this, if you're trying to make something beta insensitive, this is a very poor way of doing it. Why? Because collector current, what you're doing is you're deriving collector current from base current, and base current through this beta relationship. And base current is what you're fixing through VCC, 0.7 and RB. So you've made your base current, which is pretty stable. Supply voltage is stable. 0.7, let's say, doesn't change too much. RB is stable. And so base current is pretty stable. But then collector current is derived from base current through beta. And therefore, the collector current then would vary a lot. All right. So this is not a good strategy to derive collector current from base current. Making base current stable and then saying collector current is beta times IB, and that's how I'll bias. If beta is varying by 100%, my collector current would vary. The alternative is, look at this particular circuit. It says I'm not going to derive my collector current from base current. It says I'm going to derive my collector current from emitter current. This particular strategy is different. It says I have to fix the collector current in my circuit. So it says derive it from emitter current. Collector current is beta by beta plus 1 emitter current. And emitter current is what this circuit fixes. Emitter current, when I do DC analysis, this point is 0. This point is minus 0.7. So minus 0.7 minus VE by RE gives you the emitter current. So this circuit says the following. Fix the emitter current using supply voltage and using resistors. Fix that using here. And then derive collector current from the emitter current through beta by beta plus 1. And you can see here now, because it's beta by beta plus 1, and if beta is sufficiently large, these two things cancel each other, and my ICQ has no dependence on beta. Very, very weak dependence on beta. So my stability is very high. So it's a way of how do you derive. In this case, you're deriving it from base current, and you end up with a poor circuit. And in this case, you derive it from the emitter current. And emitter current you fix through your supply and resistors, and then your collector current is very insensitive. Okay, so it's a very nice circuit that the dependence of collector current on beta is almost negligible, right? But what is the price that we have to pay? Well, an extra supply voltage. an extra supply voltage, and that too a negative voltage. If I have 5 here, I may require -5 here. So in a negative voltage, if it were a positive voltage, let's say instead of 5 here, if I were requiring 3 here or something like that, positive voltage, I could have derived it from the main voltage itself through voltage dividers or whatever. But this is a negative voltage here. So another power supply. So that sort of complicates, but it's a very good solution. If you can afford another negative supply in your system, it's an excellent solution. IC is almost independent of the beta that you see here. But if you're still bent upon saying that no, I want a beta insensitive circuit, but I want to use only one supply voltage, VCC. All right. I want a circuit which runs only on positive supply voltage, and the circuit is still beta insensitive. What would you do? Look, there are, as you can see here, there are two ways of deriving the collector current. Our interest is in collector current, right? Either you can derive collector current from base current, or you can derive collector current from emitter current. So whatever new circuit that you're going to think of, which strategy would you follow? Obviously this one. You'll try and follow this particular strategy because it says deriving collector current from emitter current is the way to go. Now, can I derive collector current from emitter current? And the emitter current that you see here, can I generate emitter current without requiring a negative supply voltage? If I can do that, if I can generate emitter current without requiring a negative supply voltage, and using only resistors and supply voltages, whatever it is, then I have a stable value of IEQ. And from the stable value of IEQ, we generate stable value of ICQ. So the strategy is, we would still like to do the same thing, but without using a negative supply voltage. Okay? So, why don't we just get rid of it? Just remove the negative supply voltage and put it to ground. Will it work? What would happen in this particular case? Well, if you do DC analysis, what will happen? This node is ground, and this is ground. If you look at it, the transistor is not biased at all, right? I don't have voltage to forward bias my base emitter junction. So the transistor is in cutoff state. It will not work. But this is the way to go, right? I would not want any negative voltage here. So I have to remove the negative voltage. So now, so I don't want a negative voltage, but I would still want what do I want? I want to derive my emitter current through emitter resistance and some voltage here. So I have to create a voltage here and derive collector current in this manner here. So what I'm looking for is, I'm going to make this node ground. I don't want to use negative supply. I have a resistor RE, and this is how I want to derive my emitter current. And so what I want is a positive voltage at this particular point. VE has to be positive because positive would force the current down and will have the right value of emitter current, and then collector current would respond. I want a voltage at this particular node. Now, while you are thinking of voltage at this particular node here, think about the following. When I write KVL from VCC to ground, I get VCC is ICQ RC plus VCEQ plus VE. Q refers to bias point, okay? Quiescent point, bias point, don't worry about that. So drop here, and plus drop here. Is this drop important for you? ICQ RC? Well, one way of writing gain is, GMRC, and GM is what? ICQ by VT. So ICQ RC drop is very important for you. Your gain depends on this drop. So obviously, if you want high gain, you're looking for a large value. Is VCQ important for you? VCQ determines your swing. You want large VCQ also. So while I'm trying to bias, see, why do I require I'm putting an emitter resistance and all that for biasing. So I don't want a very large value here, VE, because any large value that I put here sort of takes it away from VCQ and ICQ, takes it away from my ability to get gain and swing. So I don't want a large value of VE. I want a small value of VE. So let's, as an example, suppose we, this is a budget. We allocate 2 volts to ICQ RC. This is a budget. So ICQ RC, we allocate 2 volt. To VCQ also we allocate 2 volt. Let's say we allocate 1 volt here. There are different ways of allocation depending on how much gain you want, how much swing you want. You have to allocate. You have 5 volts here. Let's say supply voltage is 5 volts, so you have to allocate. This is your budgeting. We call it supply budgeting. So much supply voltage is available. Where do you want it to drop? Across which element, how much? Okay. 2 volt here, 2 volt here, 1 volt here. That could be one possibility. So let's say I'm looking at 1 volt here. How do I generate 1 volt here? How do I generate 1 volt here? Well, so you're saying 1 volt, so 1 volt is here. So what do I require here? 1.7. Now how do I generate 1.7? All right. I have 5 volt supply here. R1 and R2. I can generate 1.7. Whatever you want, I can generate. Right? And then I connect. So VCC R2 by R1 plus R2 will give us 1.7. Then you connect it up. But the moment you connect it up, there's a problem. It's no longer a voltage divider. Can you see a problem? It's no longer a pure voltage divider is this, right? The moment you connect it up, what else happens? There's a base current starts flowing here. It's not a pure voltage divider. So this voltage that you saw here would start depending on base current and therefore will start depending on beta. So what do I do? How do I make it a good voltage divider? Yeah, you're right. If I can make the current flowing here, current flowing in this branch, VCC by R1 plus R2, much larger than base current, then whatever base current flows will not affect my node voltage here. If I can ensure that this current flowing here in this branch here is much larger than, so whether IB flows or doesn't flow, this voltage would be very stable, 1.7 volts, let's say. So that's the strategy that we follow, and we end up with a circuit like this. So note that the whole idea was, I want a voltage here, positive voltage here, stable value, which implies a stable value of 1.7, and I generate it through R1 and R2. And we use that, and we connect it up. Now we can complete the circuit. We want to apply our input also, so we use a capacitor to couple our input so that the capacitor does not affect our bias point. And note that any resistance in the emitter will cause a problem with the gain, because we want the input that you see here, we want the input to appear only across the base emitter voltage and not appear across RE. So bypass the capacitor also, bypass the resistor also. Right? So we end up with a configuration which is shown over here. A way of biasing the transistor, which if we choose things carefully, if we choose, note that R1, R2, all that have to be chosen carefully. If we choose it carefully, then this particular circuit will requires only one supply voltage, and it can be beta insensitive, and you can apply your input, and you can take the output here, and should work fine. Okay, I've added here, but the circuit is good for discrete implementation because it uses so many capacitors. These capacitors cannot be implemented on an IC, so this solution is not good for an IC amplifier. Okay, but for a discrete where capacitors are easily available, this seems like a reasonable circuit. Okay, so the previous solution I had shown you was VCC and a negative supply voltage. This solution I've shown you uses only positive supply voltage. Have we lost something in the process as compared to the previous solution? Why would anybody even consider this solution? Think about it. So have we gained everything? That we have gotten rid of negative supply voltage, so our biasing is only from the positive side and everything is working fine? Or have we lost something in the process also? Okay, think about that. All right. So this then is a very popular circuit that's commonly used, and so R1, R2 are used for biasing, and so let's quickly look at this particular solution here. So how do we do a analysis now? So far we were looking at how we may arrive at a solution like this. So how do we do analysis? Well, the biasing part is shown over here. And what we can do is we can rewrite it in this particular form. And if you want to do an exact analysis, what you can do is we can build a Thevenin's equivalent between this node and ground. Thevenin's equivalent. So open circuit voltage would be, if you break this, would be simply voltage divider. And the Thevenin's resistance looking from here, as you can see, will be R1 parallel R2. Okay, so we are building a Thevenin's equivalent circuit for this part. And so this is what we end up. VBB, RB, where Thevenin's voltage, we are calling it VBB here. Thevenin's voltage is VCC, R2 by R1 plus R2. And the Thevenin's resistance RB is R1, because this node is ground. This also becomes ground when you do Thevenin's resistance. So R1 parallel R2. So we end up getting this circuit. We can now analyze. VBB is so much here. We can write a KVL in this particular loop. VBB is IBRB plus VBE plus ICRE. Why did I put in an approximate sign? Why not an equal sign? Because this is actually an emitter current. I should have written IE times RE. But we're saying collector current and emitter current are almost equal. So that's why it's an approximate sign here. So from here, we know that IB is IC by RB. So we can, IC by beta. And we can take this and rewrite it, and we obtain an expression for IC. IC is VBB minus VBE, RB by beta plus RE. VBB is given over here. Okay. So now, this is how the circuit is biased. If you want to make it beta independent, what do we have to do? We have to make RE much, much larger than RB by beta. So this is the condition. So if I want, from this equation, I can calculate stability, percentage change in current divided by percentage change in beta. By derivatives and all that, you can show that this is equal. And basically, it is telling you is that if you want your circuit to be beta stable, you have to ensure this condition. RE should be much, much larger than RB by beta. That's what you have to do. And the more this much, much larger is, if it's a factor of 10, maybe you get a stability of 0.1 or whatever. If you can make it 100, you'll get even more stable. So depending on how large you can make RE as compared to RB by beta, the more stable the circuit would be. Obviously, you would expect the more stable I make my circuit, the larger this much, much larger factor is, I'll be losing something in my design as well. The more stable you will make, something else will be lost in performance and gain or whatever you'll see. Okay. So this is the condition then. Now note, let's explore this condition a little bit further. RE much, much larger than RB by beta here. So if RE is much, much larger than RB by beta, I can multiply ICQ on both sides. ICQ RE much, much larger than ICQ RB by beta. ICQ by beta is nothing but IB times RB. So what it is really telling, this is the Thevenin's equivalent circuit that we built. What it is really telling you is that this drop IB RB is much smaller than ICQ RE, right? That's what you need to do in order to make the circuit stable. Which means that when I write the KVL here, VBB is IB RB plus VBE plus IC RE, the IB RB drop is negligible. It's sort of negligible compared to the IC RE drop here. Look at that. Okay. So basically then, and if you recall, this is what we were, when we were designing our circuit, we said that the base current flowing through R1 and R2 should not disturb the voltage divider point. If you go back and look at what we said was, this is what is coming out. We had said that the base current flowing here should not disturb this, so we were getting this condition. This is what that condition is translating into. Okay. All right, so this is the condition here. So VBB is effectively equal to, the drop here is negligible, effectively equal to VBE plus ICRE. That's what is happening here. Now note, VBE is fairly sensitive to temperature. We know that as temperature varies, there would be a change in 2 millivolt per degree Celsius. And if there's a 50 degree change in temperature, 50 into 2 is 100 millivolt. So it's 0.1 volt change in VBE. So if you want your collector current not to change much with temperature, what you will have to do is make VBB sufficiently large as compared to VB. You can't make VBB very small. If you make it very small, then collector current would depend a lot on changes in VB. So while you're designing, what you have to do is you have to ensure this condition, RE much larger than RB by beta. That you have to ensure. And at the same time, you have to ensure that this VBB that turns out here is sufficiently large as compared to VBE. Okay? So these are the constraints that you're seeing. This is only from the point of view of stability, beta stability. This is from the point of view of temperature. So now look at this particular circuit. I want to make my circuit beta stable. And I want my circuit to be stable against temperature also. What value of VBB would you choose? This is 0.7. How much would you choose? Give me an example. This is 0.7. Would you choose 0.8? VBB 0.8? No. Obviously, everybody's saying no. 1.7? Maybe 1.7. So you would like to choose even higher, maybe 2.7. But what is the consequence? Suppose I choose VBB equal to 1.7. If I choose VBB equal to 1.7, this is 0.7. So how much is this ICRE? 1 volt. Where is this ICRE? This voltage here, 1 volt. Which means what? If VCC is 5 volt here, 1 volt is over here. What remains for your VCE and gain? 4 volt. Right? If you had chosen VBB, if you are not happy with 1.7, if you choose 2.7, ICRE then becomes 2 here. And what remains for your VCE and ICRC? 3. So whatever you do here, if you try to do that and make it more stable, you try to build this higher value, you're losing VCEQ and you're losing ICRC. You're losing gain, you're losing swing. So you can see a trade-off right there. Try to make things more stable. Well, you'll have to make the value of this particular voltage higher. VE higher. Right? VE higher, and you lose from here and you lose from here. Okay? That's the price that you'll have to pay. Okay? All right. So stability comes at the price of reduced gain, reduced swing. So all those things that you have to pay for it. Okay? So that's the trade-off. So that's depending on the design that you have, depending on the stability that you require, you have to decide. That's why I was saying, supply budgeting. How much of VE do you want to allocate here? So depending on the amount of VE that you allocate here will decide on your stability. And depending on how much VCEQ you allocate here will decide your gain, your swing. And depending on how much you allocate here, ICRC will decide your gain. So these are the trade-offs that you have to make. Stability, swing, and gain. You have to decide how much you want for each one of these things here. All right. So when we talked about this particular circuit, we know that a circuit like this is highly nonlinear. This circuit is basically similar to our normal prototype amplifier, except that it has a different way of biasing. But it's highly nonlinear. If you want to reduce nonlinearity, what you can do is, let's say you have RE equal to 1K here. Now, out of this 1K, you can have 990 ohm, which is here, and you can have 10 ohm here. Okay, so out of 1K, break your 1K into 2 parts. Most of it is here, 990 ohms, and 10 ohms is here. And 990 ohms you bypass, and 10 ohms you keep. Why? We have seen in previous lectures, 10 ohms you keep for reducing nonlinearity and reducing, improving swings and things like that. So you may arrive at a circuit like this, which contains 2 emitter resistances. One bypassed and the other one unbypassed. And each one has a role that you are seeing here. Okay? This is required for biasing, and this is required for linearity. Now, you may be thinking, why did we come to this complicated solution? Couldn't we have done another way of thinking could have been that this is my prototype amplifier. Its IC is very sensitive to beta. And so the way we arrived at the previous circuit was we said, don't derive IC from IB. Derive IC from the emitter current. And that's the route we took, and we arrived at this particular circuit here. But somebody may start from a different angle. We'll say, okay, here is the circuit. It's quite sensitive to beta. What if I use, we have said that in an earlier lecture as well, earlier discussion, that what if I put negative feedback? All of you know that negative feedback reduces sensitivity. So what if I start with this circuit and I put negative feedback into it and reduce the beta sensitivity? Okay, what if I start from that perspective rather than looking at it derived collector current from emitter current here? One way of putting negative feedback is you may think that I may take a circuit like this and put an emitter resistance here, a resistance in the emitter, and that will cause negative feedback. See if this makes sense, this diagram here. If beta increases, let's look at this one. If beta increases, its tendency is to increase collector current. If collector current increases, can you see that VE will increase? Emitter current, because I have a resistance here, so emitter voltage will increase. If emitter voltage increases, the base voltage increases. And if the base voltage increases, then the base current, VCC minus VB, the base current decreases. So we have a negative feedback. Any increase in beta would tend to increase collector current, would tend to increase VE, would tend to increase VB. And if VB increases, the base current decreases. And base current decreases means the collector current would tend to decrease. So there is a negative feedback. It looks nice. Why don't we implement this? Why don't we take this particular circuit and implement a RE here and implement negative feedback? The advantage of this particular circuit may be that I don't require another resistor. Why unnecessarily use another resistor? Why not live with this particular solution? Well, I'll leave it. If we now take this particular circuit, please go ahead and analyze this particular circuit and show that stability of this particular circuit also goes like 1 plus RE by RB by beta. Similar. If you want this circuit to be very stable, you'll have to make RE much larger than RB by beta. Same condition you'll arrive at. Well, same thing I would do. I would multiply both sides with ICQ. It means ICQ RE is much larger than IB RB. It comes to the same thing. If I write this equation, VCC start from here, VCC is IB RB plus VBE plus VE. If IB RB, which is this term, IB RB is much smaller than ICQ RE, which is VE, I can neglect this. So VCC is equal to VBE plus VE. Right? So if you want, so it looked like a nice concept, but we arrived that if we work out the numbers, if you want to make this circuit really insensitive, you arrive at RE much larger than RB by beta, and you arrive at this condition. What is the problem with this condition? Let's say I choose 5 volt here. VCC is 5 volt. VBE is 0.7. So what is the value of this node here? 4.3. The value of this particular node is 4.3. So if this is 4.3, what is left for all of this? 0.7. Out of 5 volt supply, this is coming to 4.3. What you are left with, VCE and all that, is only 0.7. A very small fraction of supply voltage you are left with to get gain and swing and all that. It's a poor solution. Right? If you want to make it very stable, you're seeing the condition that comes out to be is the drop here is negligible. You require a negligible drop. And we can understand why we require a negligible drop. Because the drop across this is IB, base current, and base current is beta. It makes everything dependent on beta here. So you want this drop to be negligible, which means that this VCC is almost VCC here, and which means that this is 4.3, very high. So this circuit doesn't work. It doesn't work. It's not practical. It may seem nice. Go ahead, put an RE in. There's negative feedback. When you work out the numbers, you require a very high value here to make it beta insensitive, 4.3 or so, which is not true for the previous circuit. I can get reasonable beta sensitivity here by making this only equal to 1 volt in this case, while this one was requiring a 4.7, 4.3. Okay. What about a different track? So this didn't work out in the sense that putting a resistance in the emitter didn't work out. We didn't get the stability that we're looking for. Are there other ways of putting negative feedback? This was also a homework problem. Look at this one. All that we do is, this looks even more elegant. Just take RB from here, remove it from here and just connect it here. No change, no extra component, nothing. Just take RB from here and connect it here. Can you see a negative feedback operative here? Look at this diagram. If beta increases, IC will increase. If IC increases, this VC, this collector voltage here, will drop because VC drops. And if VC drops here, this causes a drop in base current, which will cause a drop in collector current. So we have again managed to put a negative feedback by taking it from here and putting it over here. Okay. Again, negative feedback. Well, as I said, this is the starting point. You know, when you're thinking of a new circuit, you said, well, the strategy is going to be negative feedback. How do I put negative feedback into my circuit? The first one was by putting an emitter resistance here. Okay. Now, if you're thinking that it completely failed, the answer is no. What we have found is that yes, this particular is not working. We can take this partial solution and try to overcome this problem. Why is this VCC and why is this VE so large? And from there we can arrive, I'm not doing that, we can arrive at that if we add another R2, then the circuit works fine. So, you know, I could have arrived at this particular circuit that you see here. I could have arrived at this particular circuit through this route here. Take the circuit here, put negative feedback. The idea is good, but doesn't work out completely. And then I could have shown you that if I add another resistor here, then it becomes workable. So I could have arrived at the final circuit through the notion of negative feedback and by following this particular route. Okay, so that was also a possibility. Anyway, let's look at this. So we put it here. Now, if you go ahead, looks very nice. Now you have to sit down and do a DC analysis of the circuit, and you have to do a small signal analysis. Both of them you have to do and evaluate how good is it. In principle, looks okay. So this was a part of the homework problem. So when you look at it and you calculate the collector current, this is the expression for collector current that comes out. Now, I want my collector current to be beta insensitive. What do I have to do? What do I have to do in order to make collector current insensitive to beta? Are you seeing RB by RC has to be kept small? RB by RC has to be kept small. If I don't keep it small, the circuit will become more and more sensitive to beta. So the key to making this circuit beta insensitive is keep RB by RC small. Okay, fine, I can do that. If RC is 1K, I can choose RB equal to also 1K. RB by RC then becomes equal to 1, and then this is beta, and beta plus 2. Circuit is highly insensitive to beta. Looks like a nice solution, but don't stop here. Don't just look at IC. Calculate VCEQ also. VCEQ is also important for us, right? VCEQ determines the swing. Now, when you make RB by RC small, what do you find? VCEQ is also very small, right? I just told you, why don't you choose RB by RC equal to 1? And IC is very insensitive. If I put RB by RC equal to 1 into this, you'll get VCEQ is only 0.7 or 0.8. 0.7 or 0.8, very small VCEQ. All right, so that's what I said. All the stability that we are talking about is coming at a price. I can make this circuit very stable, you can see here, but my VCEQ would become very small. Now, VCEQ becomes very small if you're not interested in swing for whatever reason. Let's say the input is very low and output swing is required only maybe 100 millivolt. There are situations like that. Fine, this VCEQ of 0.7 or 0.8 may be okay. The other thing is, please do a small signal analysis of this particular circuit, and what you'll find is R input is R pi multiplied by RB by 1 minus AB. Please show that. Analyze this particular circuit and show that input resistance is this value here. Now, as I said, if I choose RB by RC equal to 1, so RC is 1K, RB is 1K. And let's say the gain of this circuit is 100. So this is 1K, AV is negative 100. So 1K divided by 100, this factor is only 10. And input resistance you get is 10 ohms. All right. So 10 ohm input resistance. Compared to this, you may get 1K input resistance. Let's say you are getting 10 ohms input resistance. So note that it gives you very nice stability, but VCQ is compromised. Rn is also compromised. Now there may be a place where this may be okay for you. Okay. But I'm pointing out what this particular circuit's capabilities are. Okay. All right. So let's stop, and Friday is our class quiz. So let's have this particular problem.